Hey everyone, if you've been enjoying my free math lessons on Prodigy Mathematics, I've got a great way you can support the channel and supercharge your learning. I've launched Martian Mathematics, a growing collection of problem sets, quizzes, and fully worked out solutions designed to complement my videos. These aren't just generic worksheets. Each set follows my lesson structure, reinforcing key concepts with carefully crafted problems and step-by-step solutions. Every purchase helps keep this channel running, so I can continue bringing you high-quality, free math education. Check out Martian Mathematics on Teachers Pay Teachers today. Your support makes all the difference. And don't forget to like and subscribe.
Lecture 16, Exponents and Roots. So, recall that multiplication is just repeated addition, right? So, 2 times 3 is just 2 plus 2 plus 2, which of course equals 6. But what about repeated multiplication? Well, that's called exponentiation. And how does that work? Well, I could take a number like 2, and I write it like this. And what does it mean? 2 to the third power, sometimes called 2 cubed, where 2 we call the base, and 3 we call the exponent or the power. It means 2 times 2 times 2. And what's that equal to? Well, left to right, 2 times 2 is 4. 4 times 2 is 8. So 2 cubed, or 2 to the third power, is equal to 8. It's fairly straightforward, yes? 2 squared would be 2 times 2, which is just 4. Now there are some special definitions that you should be aware of. A to the first power is just equal to A. So 2 to the first power, 2. 3 to the first power, 3. What is 7 to the first power?
7.
Good. Another definition you need to be aware of, and it's not important for the y's of this, but any number A raised to the 0 power is equal to 1 if A is not equal to 0. Now that won't be important in this lecture, but in the next lecture, where it'll be Exponents and Roots Part 2, where this is Part 1, we'll put that to use actually, okay? After squared and cubed, if we ask what 3 to the 4th power was, that's how we say it, to the 4th power. So we use cardinal numbers, 5th power, 6th power. Sometimes you can say it in a shorthand way and say 8 to the 8th. But that means 8 to the 8th power, which is where we have the base of 8 and the exponent is 8, okay? Now let's go over some important squares or square numbers. These you should know, you should memorize them, commit them to memory. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. This is a nice way to remember these two square numbers. 13 squared is 169. If you switch the 6 and the 9, then you get the next number squared, 14 squared. That's just a coincidence. It's not a repeating pattern. 15 squared is 225. 16 squared is 256. 17 squared is 289. 18 squared, 324. 19 squared, 361. And then finally, 20 squared, I guess I could have made this line up a little better, but 20 squared is 400. Now let's look at a couple of these for a minute, because there's a property here that I think is very useful when evaluating these squares. And if you forget some of them, then it will be helpful. Let's look at 12 squared, for example. So what does that mean definitionally? Well, 12 squared means that you're going to do 12 times 12, yes? Well, if we factor 12, who can think of some convenient factors for 12? How about 6 times 2, yes? then I can write this first 12. I'm going to use parentheses to separate the two 12s. I can write 6 times 2 times, and then the other 12 I'll also write as 6 times 2. Now through the associative property of multiplication, which means that we can associate any of these together, we could do 6 times 2, we could do 2 times 6, and also the commutative property of multiplication, meaning that we can move any of these factors around if we please. We can move the 2's together and the 6's together, so we can rewrite this as 2 times 2 times 6 times 6. You see that? Yeah. And, well, what is 2 times 2? That's just, by definition, 2 squared. And what is 6 times 6? Well, that is, by definition, 6 squared. And so you see that we can write 12 squared as 2 squared times 6 squared. Another way to think of this is we could have said, okay, 12 squared is equal to 6 times 2 squared, the whole thing. And it turns out that one of the properties of exponents, which we'll learn more about in the next lecture, is that if you raise product to a power, then you can apply that power to each of the products, or each of the factors individually. So you can write 6 times 2 quantity squared as 6 squared times 2 squared. Now why is that useful? Because if you just remember some of the smaller square numbers, like 2 squared is 4 and 6 squared is 36, then you can evaluate 12 squared. Because 36 times 4, well, what is 36 times 2? If we double 36, we get 72. And if we double 72, what do we get? 144. Nope, 144. Very good. So 36 times 4 is 144. So we can evaluate some of these that we might forget that are factorable. Now, it won't help you with like 17 squared because 17 is a prime number, and it can't be factored other than to write 17. 19, the same thing. 13, also the same thing. But 14 and 15 and 16 and 18, and of course 20. 20 is an easy one because that is just 2 times 10. And 2 squared is 4, and 10 squared is 100. 4 times 100, 400. But, you know, again, you should really commit at least these to memory. If you have trouble with that, then at least try to get up to 12. But if you can get up to 12, then you can easily get 13 and 14 because of this funny relationship, 169 and 196. There are also a few cubes you should remember. Not this many, but let me write those down. So important cubes. 2 cubed. Well, now, and this is, I'm going to show you the trick if you have trouble remembering some of the cubes. Remember that this is, by definition, 2 times 2 times 2. Yes?
Yes.
And I can rewrite that as 2 squared times 2. So I can always write it in terms of a square number, which hopefully I know. 2 squared is 4. And so if I want to evaluate what 2 cubed is, I can say, well, that's just going to be 2 times 2 squared, or 2 times 4. So it's 8. Similarly, 3 cubed, well, that's going to be 3 squared, which is 9, times 3. So this is 27. 4 cubed, well, that's going to be 4 squared, which is 16, times 4. So if I multiply 16 times 4, who knows what I get?
64.
So we get 64. 5 cubed, I think we just did that one. That's 25 times 5, which would be half of 250, which is 125. All right, 6 cubed, that's going to be equal to 6 squared times 6, which is 36 times 6. And what is 6 times 3?
18.
So 6 times 30 would be 180. Plus, what is 6 times 6? 36, of course. What's 180 plus 36? That's going to be 216. 7 cubed, which is 7 squared times 7, which is 49 times 7. And again, 7 times 4, or 7 times 40, rather. Anybody? 280 plus 7 times 9 is 63. Who can do 280 plus 63? 343. And then 8 cubed, which is 8 squared times 8, which is 64 times 8. You can double 64 3 times. What do you get? If you double it once, what's 64 times 2? And then 128 times 2? 256. And 256 times 2?
400.
No.
500.
512. 9 cubed? That's going to be 9 squared times 9, which is 81 times 9. And what is 80 times 9? What is 9 times 8?
72.
So 720 plus 9 times 1 is 9. So we get 729. And then finally, 10 cubed, which is 10 squared times 10, which is 100 times 10, which is just 1,000. So if you remember cubes up to 10 cubed, right, that gets you a pretty wide range of cubes to draw on. Now I'd like you to try one. Try and compute. Remember we said that 20 squared was 400, right? Well, what about 21 squared? How can we crack that just by using the knowledge of square numbers that we have at our disposal thus far? So go ahead and pause the video, try that at home now, come back when you have your answer. Well, what I recommend doing is factoring 21. Who can think of a convenient factor for 21? Factors for 21. Something times something is 21. What? 7 times 3. So we can think of this as 7 times 3 all squared, which of course means, from what we said before, that this will be 7 squared times 3 squared. Yes?
Yeah.
Well, what is 7 squared? 49. And what is 3 squared? 9. So we have 49 times 9. 9 times 40?
36.
Well, 360, right? Because it's 40, not 4. So that's 360 plus, what is 9 times 9? 81. What is 36 plus 8?
44.
44. So 360 plus 80 would be 440. And then plus that one more, because 0 plus 1 is 441. So we get that 21 squared is 441. Where are you going to see exponents? Well, you're going to see them everywhere if you get to algebra. Polynomials are filled with exponents. If you think of geometry, like area, what is the area of a square of side length L? L squared, right? A cube of side length L would be L cubed. Okay, so we'll see that. We'll do a little bit of geometry in a later lesson. And so we'll see those exponents there. But another place that it comes in really handy is in prime factorization, which we've already done. Let me show you. So if I wanted to factor 16, factor 16, and I want to do a prime factorization. And so what we would do is we'd create a factor tree. 16 is even, so we'll start with the prime number 2, which goes into 16 8 times. But 8 is even, so we can pull out another 2, which goes 4 times. And 4 is even, so we can pull out another 2, which goes 2 times. Since the nodes of my tree now have all primes in them, I have my answer that 16 is just 2 times 2 times 2 times 2. But man, that's a lot of stuff to write, yes? So exponents help us out, because we can then write this as simply 2 to the 4th power. Let me give you one to try. I'd like you to factor 72. I want the prime factorization of 72. So do a factor tree and write it out and use exponents to get the shortest possible answer that you can. Pause the video, do that now. Come back when you have your answer. Well, 72 is even, so we can pull out a 2. What is half of 72?
36.
36. Also even, so we can use our prime factor 2 yet again. How many 2's go into 36?
18.
18. Still even, so we can use another 2, pull out another 2 again. How many 2's go into 18?
9.
Good, 9. 9 is not even, so we have to jump up to the next prime number, which is 3. Can we get 3 into 9? Of course we can, and it goes 3 times. And since all of our nodes are terminated with prime numbers, we're done. So we can write this as 2 times 2 times 2 times 3 times 3, but the easy way is we see 1, 2, 3 2's. So this is equal to 2 cubed times, we see 2 3's, so that's 3 squared. I think in the last lecture we talked about negative numbers, right?
Yes.
Yeah. So let's talk about negative bases. So what if I had minus 2 squared? Anyone know how to do that?
Yes. 4.
Well, okay, very good. So we can use the definition of exponentiation as repeated multiplication. This is just minus 2 times minus 2. And we remember our rule that a negative times a negative is a positive. So this is equal to positive, and 2 times 2 is 4, so positive 4. Yes?
Yeah.
What about minus 2 cubed? Well, again, using our definition, that's just repeated multiplication. So that's minus 2 times minus 2 times minus 2. Well, we already know what minus 2 times minus 2 is. We just got that. That was 4, right? So this part here, we can just simply write as 4. So we end up with 4 times minus 2. Well, now we have a positive times a negative. What is a positive times a negative? A negative. And what is 4 times 2?
8.
8. So the answer is minus 8. Interesting, huh? Well, it turns out that if you were to try many more examples, like minus 2 to the 4th power, and then minus 2 to the 5th power, etc., you would find there's a rule. Actually, I wanted you to try one. So let me let you try one first. Minus 3 to the 4th power. So use the definition of exponentiation and the rules for multiplying signed numbers. Try that at home. Come back when you have your answer. So this is minus 3 times minus 3 times minus 3 times minus 3. So we can group these like this, I would say. Let's just group them like so. So minus 3 times minus 3, it's a negative times a negative. We know that's going to be a positive, yes?
Yeah.
And it's going to be positive what? 9, because 3 times 3 is 9. So here we get a 9 times, and this is the same thing we just did, so this is also 9. And so minus 3 to the 4th power is equal to 81, because 9 times 9 is 81. If we were to continue doing negative numbers to the 5th power and the 6th power and the 7th power and the 8th power, we'd see a pattern that would give us a rule. And here's the rule. So here is our rule. If some number b for base is less than 0, meaning it's a negative number, if b is less than 0, then b raised to the n power, where n is an integer, is positive if n is even. B to the n power is negative if n is odd. This is going to be important for what we're going to talk about next. But just think about that for a second. So I said, now I don't want the actual answer, but if I said, minus 7 raised to the 4th power, is it a positive number or a negative number based on the rule? Well, the question is 4, which is n, is that even or odd? Is 4 even or odd?
Even.
Since n is even, that means the number 7. I forgot what I said. 72 minus 72. Minus 7, minus 7. Minus 7 to the 4th power is going to be positive. What if it was minus 7 to the 7th power? Now n is odd, so it's going to be negative. All right, now like division is the inverse operation of multiplication and subtraction is the inverse operation of addition, exponentiation also has an inverse operation. So I'm going to give you a definition. So here is, I know it looks horrible as a definition, but as we use it, we'll see what it means. So it says the nth root, so the root is the inverse operation of exponentiation. The nth root of a number a, written as, we use this sign here, which is called the radical sign, we put the exponent in up here, and then a is the root that we're interested in taking, is the positive number b such that b raised to the nth power is equal to a if n is even and a is greater than 0, or if n is odd and a is greater than 0. It is the negative number minus b such that minus b to the n is equal to a if n is odd and a is less than 0. So in the next lecture, we'll talk about the special case of what happens when a is less than 0 and n is even. And so that's a special topic, and we'll get to that next time. But using this definition, let's try a couple of examples just to see what this looks like, because I think it'll make more sense once we start to unpack that. The square root of 25. Now, you don't need to write the 2 for the square root. People don't typically write things like second root, okay? And that is confusing, I agree. But when you write it like this, this means the square root. So the base we're looking for, right? Or excuse me, the exponent we're talking about is something squared. So this is equal to 5 because 5 squared is equal to 25. Now with this definition, well, let me just ask you this. What is minus 5 times minus 5, or negative 5 times negative 5? Anybody? Well, a negative times a negative is a positive, right? So it's a positive value, and 5 times 5 is 25. So isn't that funny? Negative 5 squared is also equal to 25. But the square root, for reasons that are beyond the scope of what we can talk about now, if you know algebra, it has to do with allowing square roots to be functions, and one-to-one. But for other reasons that are outside the scope of the course, we only take the positive root. So 5 squared is 25, therefore the square root of 25 is 5. So you can take that table of squares, and if I said 64, what's the square root of 64? Well, it's 8, since 8 squared is 64, you see? Let me give you one to try. Why don't you try the square root of 16? So go ahead and pause the video, try that now. You can consult that table of square numbers that we had before if you need to, if you haven't already committed that to memory. Come back when you have your answer. Okay, well, what is the square root of 16?
4.
4, because 4 squared is equal to 16. Let me give you a tough one. And this is going to take advantage of the second part of our definition here. It'll at least highlight that. I want you to compute the cube root. Now, whenever we start to get into exponents of 3 and higher, we have to write that exponent here above the radical in this little gap right here on the radical sign. You can see the n here, right? You don't write the n if it's 2. You don't write anything like this if it's 1. But for 3 and higher, we have to put that sign right here. So that means the cube root. So I'm asking the question, something cubed equals, and in this case, I want it to be equal to minus 8 or negative 8. So pause the video, give that a think, come back when you think you have your answer. Well, I already told you that we're not going to be considering, right now anyways, negative numbers under the radical if n is even. Well, here we have n being odd, right? So we're looking for something such that minus b, the base, which we don't know what it is yet, that's our answer, the base, right, is raised to the n power, in this case 3, is equal to a, where a is minus 8. So something b to the n, or excuse me, to the 3, something cubed, I can write that a little neater, is equal to minus 8. Well, how about minus 1? Would that work? Minus 1 times minus 1 is positive 1, times a third minus 1 is negative 1. Nope, that doesn't work. Let's try minus 2. Minus 2 times minus 2 is positive 4. Positive 4 times 2 minus 2 is negative 8. So we found our answer, right? Minus 2 cubed is equal to minus 8, which means that the cube root of minus 8 is equal to minus 2. And I'll put because minus 2 cubed is equal to minus 8. Okay. Let me just look at a few more of these. We're not going to need the definition to think about these next couple of problems. So I'll go ahead and erase that now. I do apologize. I wanted to come up with an easy definition that really captured all the necessary facets of roots, and that's the best that I could do. And it's terrible, I know, but I think just practicing, you're going to get the idea. If you can remember that the cube root of minus 8 is minus 2, and that whenever you're taking the square root or the fourth root or the sixth root of any number, you'll always use the positive value, even though a negative value might have worked, okay? Let's see. What about fractions? We love fractions. Why not throw some fractions in here, huh? Sounds good, right? So how would we deal with this? 49 25ths. What is the square root of 49 25ths? Well, it turns out that another property of exponents that we're really going to investigate in more detail in the next lecture is that if you have a product or a quotient under the square root sign, you can break it up into individual square roots. So this we can do. We can write this as the square root of 49 divided by the square root of 25. And what is that? Well, the square root of 49, what squared equals 49? 6 times 6 is 36. 7 times 7 is 49. So 7 squared is 49. So the square root of 49 is 7. And then in the denominator, the square root of 25, what would that be? It's 5. Very good. So the square root of 49 25ths is 7/5. How about a mixed number? That should be fun, huh? Love mixed numbers, yes. So let's take the square root of 12 and 1/4. Square root of 12 and 1/4. Okay, you're probably skeptical that we're going to find anything here, but let's see. What can we do with this? We know, since we have a mixed number, that what that means is that we're looking for the square root of 12 plus 1/4. Yes? And you might be tempted at this point, even though it wouldn't get you anywhere, to say, oh, well, this must be equal to the square root of 12 plus the square root of 1/4. I see that I could probably do something with that 1/4 because 4 is 2 squared. So I can say this is just a half, but that, of course, this is not right. It is not equal to this. It's not like when we have a product of numbers where we can take the square roots on each of the factors, or quotient where we can take the square root of the numerator and the square root of the denominator separately. You cannot separate them, okay? And we'll see more about why that is in the next lecture, but let me just point out that you cannot do that. So that's no-go. What we can, however, do is write this instead of a mixed number. We can turn this into an improper fraction and see if we can get anywhere. So this would be equal to the square root of, well, we want 12 to have a denominator of 4. So what is 12 times 4? What is 12 times 2?
24.
And 24 times 2?
48.
Yeah, so this is 48 fourths plus 1/4. And that is equal to the square root of, remember, I can't break this up into individual, a square root plus a square root. It's all under one square root sign. 48 plus 1 is 49 fourths. Didn't need that. And that we can do, right? That will be equal to the square root of 49 divided by the square root of 4. Both of those are perfect squares. And the square root of 49, as we saw before, was 7. And the square root of 4 is 2. And so this is 7/2, which is the same thing as 3½ So the square root of 12 and 1/4 is 3½. So let me end with one for you to try. I'd like you to evaluate the square root of 3 squared plus 4 squared. And I want you to keep in mind, right, that if I write the square root of 49, which we just did a minute ago, right, I could rewrite that as the square root of 7 squared, yes, which is just equal to 7 by definition. Do you see that relationship? That's kind of the right way to look at it. But I'd like you to try the square root of 3 squared plus 4 squared. So pause the video, try that now, come back when you think you have your answer. Okay, well, because this is not a fraction, so we can't like get a common denominator or anything like that, all we're really able to do, and remember we cannot separate this into two square roots added to each other. We can't say this is 3 plus 4, therefore 7, right? The only thing we can do is we can expand these square numbers. So we know how to square 3. So this will be equal to, again, the square root of 3 squared. Well, that's 3 times 3 is 9. Plus 4 squared, which is 4 times 4, which is 16. I can add those. No problem with that, as long as I keep that square root sign up there, right? What is 9 plus 16? 9 plus 16? 25. Now, 25 is one of those square numbers that we had to memorize earlier, right? Remember that 5 squared is 25. So the square root of 5 squared, by definition, is 5. Now that, 3 squared plus 4 squared, giving us 5 as the answer, is kind of a famous and important example we'll learn about when we start talking about geometry a little bit and the Pythagorean theorem. This is the simplest set of Pythagorean triples, the 3, 4, 5 combination. And so we'll see this again when we do a little bit of a geometry of triangles. Okay, so that's all I've got for you today. Just a kind of a get started with dealing with exponents, which I think you won't have any trouble with, and then roots. And those are a little bit trickier, and you have to be careful. Remember what you can do, what you can't do. We'll formalize those rules in the next lecture when we talk about it in a bit more detail. Any questions? Good? Well, that's it. I'll see you next time.